Okay, so buffer solution. Okay. Let's suppose you have some weak acid, okay? We know this is going to form an equilibrium reaction, producing very tiny amount of hydrogen and very tiny amount of the conjugate base, right? So this is a weak acid. So if it was a strong acid, and you start with 100 with the 0, 0, then in the equilibrium, change would be negative 100, and this will be like plus 100 if it is a strong acid, okay? And you'll end up with 0 here, and 100 here, and 100 here. Is that right? Does that make sense or not? Okay, so that's what happens if it's a strong acid. Now we know that for weak acid, it doesn't really do that. Typically, this will go down by 1. Not even partially. Not even partially. It's almost none of them, you know. Very little of them, okay? So this will go up by 1 and 1, and this will be 1 here, and 99, okay? So that's what happens with weak acid, okay? Now, an example for that is CH3COOH. That's ethanoic acid. That's in vinegar, right? So this produces that and that. Sorry. Like that, okay? And we talked about the Ka last week. That's the acid constant. And that one was about, let me Google that. Acid constant of ethanoic acid. It's 1.8 times about 10 to the power of negative 15. Negative 5, sorry. Okay. So what that means is that if you have 1 mole, start with 1 mole, and then 0, 0. This will go down by negative x, plus x, plus x, 1 minus x, x here, and the acid constant is the product over the reactant, and this will achieve this number, but this number is almost equal to 1, so x squared over 1 is 1.8 times by 10 to the power of 5, negative 5, so therefore x is equal to square root of that number. So this is all last term stuff, I guess. So you get about 0.0042. Yeah. 424, okay? Which means, so I gave you this example, like 100 becoming 99, right? So in fact, for this particular weak acid, you're going to, if you have got 1 mole of the weak acid, let's do 1 minus the answer. You get 0.9958. Okay, and then you're going to have 0.0042. Let's just, let's just write it like that, 0.00. It's 42. So very, very tiny amount of this and this and this, okay? And let's work out the pH for it. It'll be negative log of that, okay? Down there. So you would get pH of negative log of the answer. I'm sorry. This and then 0.004242640687. So about the 2.37. Okay. But if you had a strong acid, the concentration of the hydrogen could have been just 1, because if you have 1 mole, you're going to get 1 mole of that, right? If you had started with 100, you end up with 100, right? So if you started 1 mole, this would have given you 1 mole for hydrogen. That would have given you pH of 0. That's stronger acid than this one, much stronger. pH can be negative as well. Negative means like really, really acidic. Okay? Negative ones are really, really acidic. 0 is also really acidic. Human stomach has pH of like 1.5-ish or something like that. So it's very low. Anyway. So that's just brief revision on Ka. And figuring out the pH from it, you know. So this is the old method without the Henderson-Hazelbach equation. From Ka, you do this ice table. You construct this equation, quadratic equation. You solve this quadratic equation. Then you figure out the concentration of the hydrogen, and then you plug it into the pH formula. Then you get the pH of that. Okay. Now, what is a buffer solution? Buffer solution. That's right. But how do you make it? So buffer solution is something that resists the change in pH. Like whether you put in really, really strong acid to the solution, or you put really, really strong base into the solution, it resists. So when you put hydrochloric acid into water has pH of 7, right? But as soon as you put hydrochloric acid in it, pH will go down to like 1 or something, right? It'll rapidly go down. And if you put sodium hydroxide into water, it'll rapidly increase the pH, right? But buffer solution is something that resists that sort of change. And how do you do that? How does it do that? Because it is made of weak acid, typically weak acid, and its conjugate base. Okay? So, let me ask you this. So I've got this weak acid here. And at the moment, the concentration is of the weak, this is the weak acid, isn't it? So into water, I just put in 1 mole of this ethanoic acid. And I pretty much still have 1 mole of ethanoic acid, right? So that's weak acid here, which is fine. So to create buffer solution, you need weak acid, right? But you also need conjugate base. Do we have conjugate base? Yes, we do, but not a lot, right? So this was just what we have here at the moment is just made by into water. You just dump this weak acid, but you only gonna get pretty much just the weak acid, right? You're not gonna get many of this. Okay, so therefore what you have to do is put in the conjugate base as well. So how do you get It'll have to be roughly the same amount. Okay? Yeah. So to create an effective buffer solution, you roughly need equal amount of this and this. Okay? However, if you're only putting the weak acid, because it's a weak acid, it doesn't really produce the conjugate base. So you would have to put the weak acid as acid, but this is not going to produce any of the conjugate base. I mean, very tiny amount. So you're going to have to put in some conjugate base as well. And the ingredient could be CH3COONA. Okay.
Sorry, why are we using that salt again?
So this salt here can dissociate into, just as, NaCl as salt, right? That dissociate into this and this, right? So there is also a salt called CH3 sodium acetate. This is known as sodium acetate. This dissociates into Na+, and then CH3COO-. I'll show you a picture of it. Okay, where is internet? Okay. So it looks pretty much like regular salt, just white powder. Okay, looks like that. Yeah, it's just a white powder. I'm not sure if you can eat it. I think you can eat it. Maybe not. I don't know. I don't recommend it. All right. So it's a powder. So you put it in there. And this will produce lots and lots of this guy, right? So you have lots and lots of this one. And also lots and lots of this one. And there you go. You have pre-created buffer solution. Okay? So how does this work? How does this resist the change in pH? So let's say you have here, inside this, you have lots and lots of HAs, okay? So HA is the acid, okay? The weak acid, all right? And also you have lots and lots of conjugate base. That's your buffer solution, okay? So HA represents your acid, and then A- represents this, okay?
Yeah, okay.
Now, let's say this gets attacked by HCl. So acid, strong acid, is added to it. Then what happens is the strong acid was going to combine with the base. And because this is a weak acid, this is very good at attracting the hydrogen to itself, right? So this will, yeah, it becomes the weak acid. See? And this, the acidity all depends on the hydrogen ion. This one creates lots and lots of free hydrogen ions. But this this conjugate base is a strong base, because that's created from weak acid. Remember this? That's a weak acid. Weak acid creates strong conjugate base. Strong base means it's very good at attracting hydrogen. Okay? So when these free hydrogens are introduced to the solution, the conjugate base here, which is strong, attracts these hydrogens and say, you're not going anywhere, okay? And binds into this weak acid. Okay? So it'll make sense to you? And leaves behind the Cl minus. So effectively cancelling the hydrogen ions so the pH doesn't go down. Okay? Let's suppose we introduce sodium hydroxide. So it's a base now. So if you introduce the base, now it's time for the weak acid to take care of this guy, okay? So when you introduce sodium hydroxide, you're introducing lots and lots of hydroxide, which will increase the pH to basic, right? Then this one will combine with this one here, NaOH. So this acid versus base reaction, and we talked about this last time. Even though this is a weak acid and that's a strong base, it's still 1-to-1 reaction.
Okay.
Just because this is weak doesn't mean you need like more than one to react with this one. Yeah, it's 1-to-1 reaction. You don't need three weak acid to attack, to cancel one strong base.
That you're gonna get the basics solved.
Yeah, so this will react with this and create water. And this salt that we saw before. Okay? So this and this will react, and this will react, okay? To create water. And it's the hydroxides are gone. Hydroxides are just absorbed by this hydrogen and become water. Okay? I think you can think of this in terms of Le Chatelier principle. Have you heard of it before?
Yes. Like as in.
Yeah, so if you got CH3COOH in equilibrium with the hydrogen and CH3COO minus, so that's the buffer solution. You got lots and lots of this, lots and lots of that, very tiny amount of this, okay? And if you introduce lots and lots of hydrogen, okay? So if the concentration of this goes up because of the presence of strong acid, then by Le Chatelier principle, it opposes the change, right? If the concentration of the product goes up, then it'll shift to the left, right? So this will combine with this, increase the amount of this, and then we'll return back to this side, shift to the left. So that's one way, that's another viewpoint to understand this one in terms of the equilibrium position. If you introduce lots and lots of hydroxide, in that case, because the NaOH is not part of this reaction, so I don't think we can interpret, we can think of this reaction in terms of equilibrium. But anyway, that's the point, okay? So that's pretty much everything, pretty much the theory behind buffer solution. So I guess we can do some questions now on buffer solution. Okay. Buffer solution with the pH of 4.7 was made by mixing 500 ml of this much concentration of that and 500 ml of so equal concentration, equal volume, same amount, okay, of the sodium acetate. So exactly the same ingredient, okay? So here's the buffer equation. So slightly different from mine. Mine was CH3COOH turning into, I'm not sure what that pi symbol is, That might be just a typo. So I just had that with hydrogen and the acetate, right? Same equation as this one, okay? Now, let's first of all prove. Let's just think about why this is 4.7, okay? We know that the Ka for this is like 1.8 times by 10 to the power of negative 5, right?
Sorry, how do we know that? Just like...
It's just a published data.
Oh, okay, right.
Okay. Yeah. And then initially the concentration is 0.5 because you have concentration of that, okay? And you have concentration of that, which is 0.5 here. And you start with 0, right? I guess. Now, this will go through some change, I don't know, but I guess some of this will, I mean, because there's nothing here, this will shift into these two. So it has to shift to the right because there's nothing there, almost nothing. So this will be 0, negative x plus x plus x. And at the equilibrium, it will be 0.5 minus x. This will be x here, and this will be 0.5 plus x. But this x is, again, very, very tiny amount. Okay? Yeah, because this Ka is such a low number, isn't it? So the product of these two over this one is this number. So this has to be very, very small number. Anyway, so the this one times by this one over this one, 0.5 plus x times by x over 0.5 minus x is equal to 1.8 times by 10 to the power of negative 5. And again, this number is almost 0.5. This number is also almost 0.5. So you can just abbreviate this as just 0.5 times by x over 0.5. Then you get x is equal to 1.8 times by 10 to the power of negative 5. And that's your probably concentration of this. So if that's the concentration, then what's the pH? Negative log of 1.8 times by 10 to the power of negative 5. Then you get about 4.7. You never done this stuff before, but I think you will soon, okay? This is part of the Year 12 curriculum. Okay? Yeah. Anyway, so for this test, you may not be dealing with this, and you can see that the sample test doesn't... what I just did here was to show you where they got this number from. Okay? Yeah. But if you don't need to know this for your exam this time, but you will for your next one, I think. Okay? Now, so here's your buffer solution. So you have equal amount of the acid and the weak, the conjugate base. Now the first question. The first question is, the addition of 10 ml of this much mole per liter of sodium hydroxide would raise the pH of the buffer solution by consuming the hydrogen plus ions. Well, that's right. If you add the base, then of course the pH would go up. But not so much in this case, of course, right? Is this on a statement or what? Is it a question or a statement? The addition of...
it's true or false on each one of them.
Is that a true or false question? Let's think about this again. That's a statement there. Additional the addition of small quantities of hydrochloric acid will force the equilibrium to shift to the left by favoring the reaction that are partially counter. So these are all statements, right?
You need to choose which one's most accurate.
Yeah, so let's go for A first. The addition of 10 ml of this much concentration. So this is a small amount of strong base, right? Concentration is lower and the volume is lower than any of these. So it's a very small amount of base compared to what's available. And of course, the base will react with the acid, right? Conjugate, the weak acid will take care, will help maintain the pH when this strong base is added. So addition of that would raise the pH of the buffer solution by consuming the but no, not really. Okay? Because in this reaction, in this equilibrium, you have lots and lots of this and lots of that. You don't not enough this one, okay? There are not many this. Okay? So what's the concentration of, think about this.
Are you making that observation because the pH is like pretty like high for an acid? Like,
No, just have a look at this number. So you see, they give you the pH is 4.7, right?
so it can't be that acidic.
Figure out the concentration of the hydrogen. That's 10 to the power of negative 4.7, right? So that's 10 to the power of negative 4.7, and you get this 1.2 times by 10 to the power of negative 5, which is pretty much this number, right? So what you've got is 0.00002 mole per liter. That's the concentration of the hydrogen. However, you are adding this much concentration, this much mil. So what's the number of mole of a hydroxide? The concentration, actually the concentration, you don't have to multiply these two. We're just looking at the concentration. That's 0.01. Have a look at that. Actually, let's figure out the actual number of moles. The number of moles of hydrogen is concentration times the volume. So I'm going to multiply this one. So times by volume is going to be 1 liter, 500 mil, 500 mil. So you got to multiply by 1. So this is, yeah, so there are 0.00002 moles of the hydrogen. Hydroxide, you have 0.01 times by volume, 0.01. So you have 0.01 times 0.01, right? So you have 0.1234 and then 1. So that's way more than this one, isn't it?
Yeah.
You have way more. So is it really? I mean, just take a look at this sentence here. It says that what that sentence is saying is that this would eat out this one, and that's the reason why the pH would go up.
Yeah, that's correct, right?
Well,
because there's way more. I mean, the concentration of OH is way more than.
Well, this is way more than that.
So it is going to.
But this is not. This is not really gonna eat out this one. This isn't going to really react with this one. This is actually. This outnumbers the existing hydrogen, of course, but this is outnumbered by the ethanoic acid. This will be cancelled off. It's not really going to increase the pH. It can increase the pH slightly, just slightly, okay? We can work it out, but it's not going to change much. This is a buffer solution.
I don't understand how you come to the conclusion that there's more of CH3COH because there's clearly way less moles of H plus than OH minus.
Well, we created this solution through dumping lots and lots of this one and lots of this one. There was no hydrogen. We worked out this hydrogen concentration as a result of introducing those two. We still have 0.5 mole and 0.5 mole. There are huge number of moles of ethanoic acid and the acetate ion. All right. So when you are dumping your sodium hydroxide, of course that outnumbers the number of hydrogen ion, but like before these guys can eat out these tiny number of hydrogens, these guys will be eaten out, okay, by the acid here. Okay. Yeah, the base, this tiny amount of base introduced, is outnumbered by this weak acid here. So this first of all, this doesn't really raise the pH. Okay. And does it consume the hydrogen ion? Well, not really. It doesn't consume hydrogen ion. It gets consumed by the acid.
Okay.
All right. So I would say this sentence is not quite right. Okay? It's not quite right. Okay? I mean, like, if you don't have any weak acid and you only have the acetate and the hydrogen ion, then of course the hydrogen ion will be consumed by this huge number of hydroxide. Then this sentence will be correct. See? When you introduce the hydroxide, it would raise the pH because it'll consume the hydrogen ion, and the remaining hydroxide concentration that will raise the pH. Okay? But not when there is weak acid, okay? Does that all make sense to you?
Okay. See, if it was a strong acid, then it would be the other way around.
That's right. If strong acid is added, then it would not it would be just consumed. It's not going to attack this one or anything else. It will be consumed. Okay? When you have a buffer solution, when strong acid or strong base are introduced, they get consumed. They don't consume. Okay? Make sense?
Yeah. Okay.
The addition of small quantities of hydrochloric acid
So yeah, this is what we talked about. Right?
will force the equilibrium to shift to the left. Yeah, so this is what we talked about here. Like in terms of Le Chatelier principle, when you add the hydrochloric acid, you are increasing this population, right?
Yeah.
That'll cause this thing to combine and shift to the left, right?
Left.
Yeah, it'll shift to the left. Yes, if addition of small quantities of hydrochloric acid will force the equilibrium shift to the left by favoring the reaction that partially counteracts the increased it counteracts the decrease in pH, because when you introduce hydrochloric acid, yeah, so up to I would say everything up to here is fine. It shifts to the left, okay? But from here it doesn't make any sense to me. By favoring the reaction, because when you are adding hydrochloric acid, that doesn't increase the pH. That's trying to decrease the pH, right? Yeah. Yeah, so this doesn't make any sense to me. See, addition of any amount of sodium hydroxide solution will not greatly change the pH. because this is a buffer solution. Any amount? No. It shouldn't exceed the amount of the acid, weak acid, okay? So because it says any, I would say this is wrong, okay? If it's a large amount, of course, this will all get consumed, okay? This will all run out. Then it'll just increase the pH. So addition of small volume of low concentration of is that called what's it called? Is that nitric acid? Would not greatly alter the pH of the solution, but the concentration of the acetate ion would decrease. That's right, because this acid will react with this conjugate base and will increase the population of this guy. It'll decrease the population of this one because this and this will combine to give this. Okay, so D is the correct choice. So this one's not a...
Oh, right. So it's going to be the other way around, right? Okay.
This one is not a buffer solution question, but it's very important. Yep. So pH plus POH adds up to 14. So if you can take in a cheat sheet or something, got to write it all down, okay? And also pH is negative log of this one. And POH is negative log of the hydroxide. So we're looking for, and also the hydrogen concentration is 10 to the power of negative of pH. Hydroxide concentration is 10 to the power of negative POH, okay? So pH is 4.2, so therefore POH is equal to 9.8. Okay? Therefore the hydroxide is 10 to the power of negative 9.8. And if you do 10 to the power of negative 9.8, then you get 1.6 times 10 to the power of negative 10 mole per liter. Okay. So I would say B is the answer.
Okay. So that's closest, because?
Yeah. So why 2 instead of 1.6? They could be just rounding it. But also this question says it was boiled, right? I'm assuming celery, when you blend celery, then it contains I don't know, some acid in it. That's why the pH has gone down. So, but you can see natural water at 25 degrees Celsius, we talked about this last time. The concentration of hydrogen is 10 to the power of negative 7. And hydroxide is 10 to the power of negative 7 also, right? Remember this stuff?
Yep.
So so this doesn't mean celery contains some hydroxide. It doesn't. It's just that the acid concentration has gone up. So this naturally existing hydroxide amount, which is 10 to the power of negative 7, is now gone down to 1.6 times 10 to the power of negative 10. So the hydroxide, the amount of hydroxide is even less than it exists in neutral water. Does that make sense to you? Because this times by this has to be 10 to the power of negative 40. But anyway, this one is I think a stupid question because it doesn't tell us what temperature it is. because it was boiled.
Ah, yeah, okay, and that changes the pH, doesn't it?
That changes the self-ionization value. So I'm assuming that this has cooled down to 25 degrees Celsius. Okay, because this only works at 25 degrees Celsius. At like 50 degrees Celsius or something, they could be like 10 to the power of -6, 10 to the power of -6, you know? In that case, pH of 6 would be neutral. All right. So it says it was boiled. Maybe because of that, because it's a bit warmer. That's why instead of this amount, it could be this amount. Okay. Because it's warmer. I don't know. That might be the reason. Who knows? Okay.